Exponential models in recursive form. So for example, you invest $500 in a savings account that pays 2.5% annual interest. Write an explicit formula and a recursive formula to model the situation. So the original investment, A sub 0, is $500. After 1 year, the value is 102.5% of the starting value. And we found that by taking our original 100% and adding the 2.5% annual interest to it. So A sub 1 equals 500 times 1.025, because 102.5% as a decimal is 1.025. And that is $512.50. After 2 years, the value is 102.5% of $512.50. So A sub 2 equals 512.50 times 1.025, which is $535.31. Each year, the value is 102.5% of the previous year's value. So A sub n equals 1.025 times the previous year's value, which is represented by A sub n minus 1. So together, this A sub 1 value and our A sub n value form our recursive definition. So we know A sub 1 equals 512.50, A sub n equals 1.025 times A sub n minus 1. Our explicit formula, which is also our exponential model, A equals our starting value, our A sub 0 of 500, times 1.025 raised to the nth power. And again, this is our exponential model, also known as our explicit model. And the 1.025 came by what we were multiplying each previous value by. Example 2. An employee buys a new computer for $1,200. Each year, the value of the computer decreases by 20%. Write an explicit formula and a recursive formula to model the situation. So the original value, V sub 0, is $1,200. After 1 year, the value is 80% of the original value. That's 100% minus the 20% that it depreciated. So V sub 1 equals 1,200 times 0.8, which is $960. After 2 years, the value is 80% of $960. So V sub 2 equals 960 times 0.8, which is $768. Each year, the value is 80% of the previous year's value. So V sub n equals 0.8, that's 80% as a decimal, times the previous year's value, which is represented by V sub n minus 1. So our recursive model or definition comes from our first term, V sub 1 equaling 960, and V sub n equaling 0.8 times V sub n minus 1. Our explicit model or exponential model, our value is our original value, our starting value, V sub 0, 1,200, times our 0.8 raised to the nth power, where n is time in years. Example 3. The table below shows the number of subscribers to an artist's photo sharing account over a period of several months. Write a recursive formula to model the data, and then write the explicit model or exponential model for the data. So our first row will contain months. Our second row will contain subscribers. We'll have months of 1, 2, 3, 4, 5. And in month 1, we had 7 subscribers. In month 2, we had 21 subscribers. In month 3, we have 63 subscribers. In month 4, we have 189 subscribers. And in month 5, we have 567 subscribers. So this is our table of data. Our A sub 1 term is 7, A sub 2 is 21, A sub 3 is 63, A sub 4 is 189, A sub 5 is 567. And each time we are multiplying the previous term by 3 to get the next term. So our recursive definition, we take A sub 1, which is 7, and then A sub n equals 3 times the previous term. So A sub n equals 3 times A sub n minus 1. Now, sometimes notation is slightly different. We might represent months as x and the number of subscribers as f of x. So here we could write the recursive definition as f of 1 equals 7, and f of x equals 3 times f of x minus 1. Okay, let's look at our explicit definition, or formula. A sub n equals our starting value, our first term, in this case, A sub 1, which is 7, times our multiplier, which is 3. This is our growth factor, or the common ratio. So 3 to the n minus 1 power. And this time, it's to the n minus 1 power instead of n, because we don't have A sub 0. We're starting with A sub n. We're starting with A sub 1. So our starting value was 7. We don't know what A sub 0 is. And if you want to double check that this is giving us what we already found, if we use the formula, so n is 1, we have 7 times 3 to the 1 minus 1, which is 0. Then we have 7 times 3 to the 2 minus 1, which is 1. And 63 is 7 times 3 squared, which is 3 to the 3 minus 1, which just gives us 3 squared. Or 7 times 3 to the third power for A sub 4. And A sub 5 is 7 times 3 to the fourth. So 0 was 1 less than our n term. 2 minus 1 gave us the 1. The 2 came from 3 minus 1. The 3 came from 4 minus 1, and so on. Let's look at a fourth example. The number of E. coli cells in a petri dish over a period of several hours can be found using this recursive formula. A sub 1 equals 16, and A sub n equals 2 times A sub n minus 1. Write an exponential model for this data. So if we look at some terms in this sequence, we have A sub 1 equals 16, A sub 2 equals 2 times 16, which is 32, A sub 3 equals 2 times 32, which is 64, A sub 4 equals 2 times 64, which is 128. So A sub n, we'll take our A sub 1 value, 16, and each time we are multiplying by 2. So that is our growth factor, or our common ratio. So times 2 to the n minus 1 power, because we are starting with A sub 1, not A sub 0. What would A sub 0 be if we had an A sub 0? Well, the pattern to get the next term is to multiply by 2. So if we took 1/2 of A sub 1, 1/2 of 16, theoretically A sub 0 is 8. So we could also write A sub n equals 8 times 2 to the n power. These should both give us equivalent values. So here, if we look at a sub n equals 16 times 2 to the n minus 1 value, a sub 1 equals 16 times 2 to the 1 minus 1 power, which is 16. A sub 2 is 16 times 2 to the 2 minus 1 power, which is 32. A sub 3 is 16 times 2 to the 3 minus 1 power, which is 64, and so on. And if we look at the second expression, a sub 1 will be 8 times 2 to the 1 power, which is 16. A sub 2 will equal 2 times 2 squared, which is 32. A sub 3 will equal 8 times 2 cubed, which is 64, and so on. So either one of these two formulas is considered our explicit or exponential model for this data. And we could also write it using different variables as y equals 8 times 2 to the x. So in general, a recursive definition has two parts. It has the definition of the first term, a sub 1, and it defines a sub n as r times a sub n minus 1, where r is the growth or decay factor or the common ratio. They're all different names for the same term. Our explicit formula, or our exponential model, can be found writing a sub n equals a sub 0, the original amount, times r to the nth power. And r is, again, either the growth or decay factor or the common ratio. We could also write this explicit formula as a sub n equals a sub 1 times r to the n minus 1 power if we don't have our original value a sub 0.